Imagine a single isolated electrical charge sitting in an empty void. If we want to map its influence, we draw its electric field, a set of sharp, radiating arrows pointing outward in every direction. As glowing point charges appear one by one, their field arrows intersect and clash. This creates a tangled, glowing mesh of lines. To find the total electric force in this space, you cannot simply add the numbers together. Because electric fields are vectors, meaning they have both a magnitude and a specific spatial direction, calculating the total field at any given point requires breaking every single arrow down into its x, y, and z components using trigonometry. With enough charges, the math quickly becomes a geometric nightmare. Let's look at a much simpler tool, electric potential. When we switch to potential, the jagged vector arrows snaps into smooth, glowing spheres of light around each charge.
Electric potential is a scalar, a simple number representing energy, with no direction attached. Instead of wrangling angles and geometry, those floating numbers representing potential simply fly toward a central point and merge into a single sum, 5 plus 2 minus 10. By shifting our focus from field vectors to potential scalars, we trade complex trigonometry for basic arithmetic. This straightforward addition is called the superposition principle. It dictates that the total potential at any point in space is simply the algebraic sum of the potentials produced by each individual charge. This animated diagram shows a clean 3D coordinate grid with a test point P at the center. Around it, we have placed individual charges, Q1, Q2, and Q3, at varying distances, marked by glowing dashed lines labeled R1P, R2P, and R3P, connecting them to point P. To find the potential from the first charge, Q1, we use the standard formula. The potential, V1, equals the charge Q1 divided by its distance to P, scaled by a standard physical constant. To account for the rest of the system, we just keep adding. The contributions from Q2 and Q3 stack up linearly, building out an extended equation across the top of the grid. This high-contrast image shows the professional version of that exact math. Because that bulky physical constant applies to every term, physicists factor it out. They use a summation symbol, the highlighted sigma, to represent adding up the ratio of charge to distance for every piece of the system. This principle allows physicists to calculate the electrical environment of any discrete charge arrangement, no matter how lopsided, clustered, or spread out the charges might be. In the real world, we rarely deal with perfectly isolated points. Instead, we see millions of charges packed closely together. As this field of tiny glowing points vibrates and melts together, it forms a single, seamless, solid object. This creates what we call a continuous charge distribution. This diagram shows how we handle that solid shape by introducing charge density, represented by the Greek letter rho. Charge density is simply a measure of how tightly packed the electrical charge is within a specific area. We then divide the 3D wireframe of the object into microscopic cubes, labeling each tiny volume element rho delta V. Because we now have an infinite number of these tiny charged slivers, the discrete summation symbol from our previous equation stretches out to become a continuous integral sign. The resulting calculus might look intimidating on a chalkboard, but the core logic remains exactly the same. We are still adding up simple scalar values to find the total potential. This scalar approach perfectly resolves one of the classic paradoxes in electrostatics, the charged spherical shell. Imagine a hollow, perfectly spherical metal shell with a uniform electrical charge spread across its outer surface. Look at this animated diagram of the shell cut in half. Outside, the electric field arrows point strongly away from the surface, but inside the hollow cavity, the space is perfectly black. The electric field here is exactly zero, because the forces from the surrounding charges on the shell cancel each other out perfectly. If the electric field inside the shell is zero, what happens to the electric potential? Remember that potential is defined by the work required to move a charge against an electric field. As a small test charge drifts slowly from the center of the shell to the inner edge, it encounters no force lines. Pushing a charge through a zero electric field requires exactly zero work. This image highlights the result. Because no work is done moving around inside, the potential never changes. As the textbook rule states, the electric potential is constant everywhere inside the shell, matching the exact value it has on the outer surface.
A zero field does not mean zero potential.
The scalar nature of potential lets us map hidden physical environments, like a solid conductor's shielded interior, that the electric field leaves completely invisible.